Hi, I'm Hiroki from Datachain, Japanese tech company focusing on cross-chain solution. I'm working on various cross-chain POC using our interoperability framework as software engineer. This is the agenda. First, I'd like to introduce a bit about our company, Datachain. We provide interoperability solutions, for example, developing cross-chain framework for interoperability among various blockchains, contributing YUI project to Hyperledger Lab, working on various POC for enterprise use like trade finance. This is the overview, basic architecture. Our interoperability framework is based on IBC and layer, and cross-chain application can be implemented easily using our framework. As you guys know, IBC stands for Inter-Blockchain Communication Protocols. There are various approaches to achieve cross-chain. One of the advantages to use IBC protocol with a layer is that system doesn't need to depend on trusted third party. Our layer sends a packet by exactly once per se. This is a brief introduction about IBC before talking about cross-framework. Roughly speaking, IBC is similar to TCP/IP. Application layer and tau layer is separated. IBC has abstractions like channel, connection, and these are used for handshake to realize reliable communications among chains. First, write client is created on each of chains by layer. Write client tracks the consensus states of other blockchains along with the necessary proof spec to properly verify proofs against the client's consensus state. Then, handshake starts through IBC connection, which allows communication between blockchain X and blockchain Y. Then, another handshake starts through IBC channel, which allows specific modules communication among connected chains. Then, each of chains can communicate through packet. Part of our cross-chain solutions are contributed into Hyperledger Lab project as YUI. The design of YUI is also based on IBC. YUI includes application modules, IBC modules, development tools, layer. For now, various IBC modules are available. For example, Hyperledger Fabric, Coda, Hyperledger Bezu, not listed here, but Ethereum virtual machine EVM-based chains can be supported. For instance, Ethereum, Cero, Harmony are under development. Next main subject, cross-framework. Cross-framework enables cross-chain transaction in Atomic on top of IBC communication. The framework provides the state store with locking mechanism and the coordinator of contract execution. Atomic Commit Protocol provides transaction coordination for multiple blockchains, enabling atomic state changes like commit and abort among chains. It works along with locking mechanism of state store. This is cross-framework composition. There are two roles, initiator, coordinator, and participants. Coordinator controls entire executions and manages participants. In this case, one coordinator and two participants. This pattern is much simpler. One of the chains works as both coordinator and participant. We often use this pattern on various POC, and there are 5 components in cross-framework. TX initiator initializes cross-chain transaction and core authenticator for authentication. After authentication done, TX runner is called to call actual contract functions. This is the actual structure of Initiate TX. Initiate TX includes chain ID, nonce, commit protocol, multiple contract transactions, signers. Contract transaction includes core info, which includes actual smart contract function. For instance, when Alice wants to swap token with Bob, 2 contract transactions contain contract function. 1. Alice transfers token A to Bob on chain A. 2. Bob transfers token B to Alice on chain B, respectively. Authenticator authenticates transaction and manages this status. This authentication is performed by the accounts of signers in contract transactions. There are 3 authentication methods. SignTX authenticates transaction by TX initiator chain. IBC SignTX authenticates transaction on each of chains respectively. Then TX initiator chain authenticates only result read by IBC packets among chains. XSignTX authenticates in any way developed. This is one of SignTX structures submitted by participants. SignTX includes TXID and signer. TXID is generated by TX initiator when initiateTX is received. TX runner executes transactions after authenticator completed authentication successfully. As atomic commit protocol, two-phase commit and simple commit is supported. I explain later. Contract manager manages contract module which implements the contract and state store, and it provides commit and abort API for state changes. These APIs are called by TX runner. Contract module defines the actual smart contract. About how each of the components works as one scenario. First, client A sends initiate TX to chain A, then transaction initiator receives it, then authenticator authenticates it. At this moment, initiate TX is signed by client A first, but authentication is not completed yet. Next, client B sends IBC signed TX signed by client B. Then IBC signed TX is read by layer to chain A. Then authenticator on chain A authenticates it. In the end, all authentication is completed. Then transaction runner is called by transaction initiator. Atomic commit protocol. Atomic commit protocol allows set of multiple operations to be executed as single operation. For now, two-phase commit protocol and simple commit protocol are supported. This flow explains about two-phase commit protocol. It executes a two-phase flow of commit request and it commits between the one coordinator and multiple participants. This commit consists of 4 steps. First, initiate step. Initiate TX is submitted to the coordinator chain. Then IBC signed TX is submitted to the participant chains. Then relayer relay packet with message IBC signed TX to coordinator chain. After authenticated, the initiate chain creates the packet prepare request then prepare commit to each of participant chains. Next, prepare step. After packet validated successfully, each of participant chains executes the contract function included in packet prepare. If execution succeeded, a lock is acquired to prevent conflicts between state changes through concurrent transactions in state store. Finally, participant chains set the status as OK and the layer sends packet to the coordinator. If the execution failed, the change status in state store is aborted, and the participant chain set status as failed. Next, confirm step. The coordinator chain receives the packet sent by each of the participant chains. Then, first, coordinator keeps waiting until all of the participants' packets received. If all of the received packets which status is OK, the coordinator sets commit to packet status and the coordinator sends a commit request to each of the participant chain. But if received status is failed, coordinator sets abort to the packet status and requests abort to each of participant chains. Then participant chains create packet. Next, commit step. When commit request is received, each of participant chains applies the change status in state store, and participant chains remove the lock and send a packet to the coordinator chain indicating completed. When each of participant chains receives abort request, participant chains deletes change status and locks and sends a packet to the coordinator chain. Simple commit protocol is much simpler. Simple commit protocol allows non-coordinator participants to avoid locking during atomic commit between two chains. The initiator chain serves both the coordinator and participant roles. First, initiate step. Initiate TX is submitted to the coordinator chain for validation and authentication. Then IBC signed TX is submitted to the participant chain. Then related packet including message IBC signed TX is authenticated on chain A. Next, prepare step. Coordinator and the participant chain A executes contract transaction in initiate TX. If execution succeeded, the lock is acquired to save the changes in state store and prevent conflicts among concurrent transactions. Then it creates the packet containing the information of chain B's contract function call and sends the packet to chain B. If the execution fails, the process of this transaction is terminated by abort. Next, commit step on chain B. Chain B receives the packet and executes the contract function. If execution succeeded, commit is performed, then it sets OK to packet status and sends it to chain A. If the execution fails, abort is performed, then set fail to packet status. Next, commit step on chain A. Chain A receives the packet and checks status. If the status is OK, Chain A commits change operation in the state store and removes the lock. If the status is failed, discards change operation in the state store and deletes the lock. Cross-chain calls. It is possible to receive the result of calling the control function of the other chain from the control function implemented in one chain. This is called cross-chain calls. This is example for token transfer using cross-chain calls. Deposit function which reduces balance of account implemented on chain A. Peg function which increases balance of account when deposit function in this example returns expected value implemented on chain B. Cross-chain calls allows one chain's contract to receive the results of the other chain's contract calls. In peg function, call function indicates deposit function of chain A. How it is implemented. This is a reminder. Initiate text and contract transaction submitted to the coordinator chain. Contract transaction includes return value and links. One contract transaction includes call info for deposit function which is called from the other and return value. This return value is actually used in peg function. Call function just returns this return value expected as a result of deposit function. And the other includes call info for peg function which require result of deposit function and links. This link indicates connected contract transaction index. After linked by this functionality, call function in peg function can refer to return value. For consistency, actual deposit function execution must return same value to return value. In detail of link functionality, the linker generates call result whose key is composed of call info and the signers of the callee TX and whose value is return value. Then linker reserves the cross-chain channel of the callee TX to IBC channel available to the caller. Then it sets the reserved to the call result. The TX initiator generates reserved contract transaction for the caller TX contract transaction and the call result. As summary, each expected return value is given when the contract transaction is created. Values are calculated off-chain. No dynamic on-chain execution of external contract calls, allowing for the fast cross-chain calls. Currently, it is not suitable to apply to frequently changing value, for example price oracle, because the value at the time when initiate text created are used. We will improve this to allow specifying within acceptable limits, but not implemented yet. Conflict-free data types (CDT). CDT provides data structure that can be read and written the same state in concurrency in distributed transactions. This data type CDT is inspired by CRDT, which stands for Conflict-Free Replicated Data Type. CDT has the following properties. Transaction can update a state without acquiring an exclusive lock. Subsequent transactions can update a state and perform the comparison operations under certain conditions. If the comparison operation is failed, indefinite error is raised and the transaction is aborted. And support data types and operations are integer, which has add, subtract, compares operations, grow-only set, which has add and lookup. As a returned value by operation GTE, it could be true or false or indefinite. This chart is example assertion by GDE. As condition, ERC20-based balance is expressed by integer store of CDT. Each of actions needs pre-commit and asserts that sufficient balance exists by GTE operation. If failed by operation, indefinite error returns. Each of value expresses possible range of balance as minimum and maximum. First, try to submit transaction 1, transfer 30 to Bob. The result of a comparison, minimum balance 100 and transferring 30 by GTE must be true, so transaction 1 could be executed as pre-commit. After that, current balance must be range 70 to 100. Then try to submit transaction 2, transfer 40 to Carol. The result of comparison, minimum balance 70 and transferring 40 by GDE must be true, so transaction 2 could be executed as pre-commit. After that, current balance must be range 30 to 100. Then try to submit transaction 3, transfer 40 to Dave. The result of a comparison of minimum balance 30 and transferring 40 by GDE must be in definite error because minimum balance 30 is not greater than 40 but maximum balance 100 is greater than 40 and it's under pre-commit condition. That's why indefinite error raised. In the end, final balance must be 30 by committed transaction 1 and transaction 2, but these transactions have options to commit and abort. About future work, there are several development topics for further improving Crosschain work, support for other ledgers based on IBC, more data structure for CDT, development support for docs, samples, and tools. Today's references are listed here, including tutorial to find out how to use Crosschain work. If you are interested in our solutions, please check out. That's it. Thanks for listening. Please feel free to contact us.